Okay, so now we want to do more algorithm analysis of this BFS search algorithm. Okay, so the first part of the code in the box, we just initialize all the nodes to be white and then set the DU to be infinity, set the PAU to be nil. So for this part, it's very clear that it is O OV. So why? Because we are touching all the nodes, right? So depending on how many nodes we have, and then, well, that is how many iterations we are going to do. So the first iteration, that is a OV. And then for the line 5, line 6, and all the way to line 9, and they are all O1s. So that's very clear because they are all primitive steps. And after that, we have a while loop. So for a while loop, the analysis could be a little bit hard because we have to figure out how many iterations are we going to do before that really ends, because that is a indefinite loop, right? So my first observation is, well, for the U, we are going to use the U to visit all the vertices, and but for each of the vertex, we only visit that once. So why? Well, the reason is, well, at the very beginning we enqueue the S, which is the root, right? And then on the fly of exploring the nodes, and for each of the node we dequeue, eventually we will color that to be black. So a black node won't be touched again, or I can say the black nodes won't be enqueued again. Is that right? Because we are only touching the white nodes, and when we explore a new white node, we enqueue that and we color that to be gray. But for if we see another black node, and this means the black node has already been touched, it has already been explored, we don't want to enqueue that again. So that's the reason I'm arguing that for the U, we will use the U to visit all the vertices, and for each of the vertex we will only visit that once. Okay, so the next one, how about the V? So for the V, it will be for we will visit the V for every vertex that appears. It appears in some other vertices adjacency list. Well, because for the current node U, and then for each of the V in the adjacency list U, we want to visit the V, right? So that the total number of the V, the total number of the V we have to visit, what is it? If we are using the adjacency list, what is the total number of the V we have to touch? And that is actually the total number of the edges. So why? If you go back and remember when we are discussing the storage as a memory requirement of doing the adjacency list, that is the theta v plus e, right? So well, the total number of the adjacency of the u will be the total number of the edges, or 2 times the total number of the edges, depending if we are doing the directed graph or undirected graph. Okay, so let me repeat. So for the u, the total number of the u we are going to visit will be the total number of the vertices, and the total number of the v we are going to visit will be the total number of the edges. Okay, so, well, what will be the running time then? So we have, let me see if we can write here. So if we if we want to consider the first 4 lines of code, and then that is OV, and we have already discussed it. Okay, and then for those part of the code, and they are all O1s. Okay, and then the next part, we are using this iteration to visit all the nodes and all the edges. So that is OV plus E. Okay, so if we add those 3 parts together, so OV plus O5, and then plus a OV plus E, and then eventually we will get this. So that is the time complexity of the BFS. Well, please notice that now we have some number of the edges, we have some number of the vertices. So we won't use the ON to express it. So instead, we have two numbers, the number of the edges and the number of the nodes. So we are going to express the time complexity of the BFS as the OV plus E. And V is the number of the vertices, and E is the number of the edges. Okay, so the next part, well, for the BFS, it calculates the shortest path distance to the source node or to the root of the tree. So we can prove that for each of the paths, well, for each of the node, since we have already built the tree, and then for each of the node, we can go back to parent again, and eventually we will go back to the root, right? And this path from all the possible nodes to the root, that is the shortest path distance. That is the number of the hops from the current node to the parent, and then to the all the way to the root will be the shortest one. Okay, and the next part, we also build a breadth first tree, and we are generating a tree structure based on the graphs by keeping part of the edges. Okay, and that is a breadth first tree structure. And as a result, since we have already analyzed the algorithm, so to build a BFS tree structure, and then and at the same time calculate all the shortest path distances, well, they can be done with the O, V plus E time. Okay, so that's the end of today's lecture.